Hello everyone, here is your lesson on the beginning of chapter 4. This is a section that has a lot of repeats of what you've studied previously, and basically it is about extreme values of functions from lesson 4.1. And basically with extremes, you're just looking at maxes and mins. That's basically what it's all about. So I'm going to start with a story problem to kind of show you the ending place we need to get to. And the textbook gives the following example at the start of chapter 4. Mileage of a certain car can be approximated by this function. So don't forget, a lot of times you're used to position and velocity and acceleration over time. This would be where a graph is your m is your y-axis, and your x-axis is no longer time, it's v, and v is velocity or speed of the car. So velocity is usually miles per hour, and mileage of a car would be like mpg or miles per gallon. So then if you're ever going to do a derivative of this, I don't know what this function looks like, but let's say it looks like this, and you wanted to try to find your maximum mileage, the derivative would be miles per gallon per mile per hour of speed of the car. So it's not exactly realistic, since it's tough to come up with equations like this, but I think you're getting the point, and I'm trying to give you a variety of functions that are not just feet and seconds or meters and seconds. So for this problem, you could obviously solve it graphically. So by placing this into your graphing calculator, and you can look at the graph, and you can pretty much figure out this answer really straightforward and easily by calculating a max or min. Now you do have to kind of consider adjustment of the window settings, and I know a lot of you like to use zoom fit a lot, which I'm not a big fan of. This is velocity of the car, that's your x-axis. So notice how I went like from 0 to 100 miles an hour. And mileage, this is probably an older problem because our book is older. I went 0 to 50 miles per gallon, but nowadays cars can get 60, 70, 80 miles per gallon depending on if they're hybrids or whatever. So here's the graph that it produces with the window settings I had. You can adjust your window settings. Make sure you look at that. I haven't talked about that too much. So graphically, you could solve it pretty simply by just calculating a maximum. Using the maximum feature of your calculator is not an approved thing you can do on the AP test. So how do we figure out that maximum? You asked, but you're probably not even asking because you probably already know where this is leading to, derivatives and calculus. And by the way, I did calculate the maximum on my calculator, and remember, here's your x and here's your y, and remember that this is how you interpret ordered pairs that are different than time. This is the speed, and this is the y value, which gives you your approximate miles per gallon when you are driving at that speed. Now basically, our calculator obviously does this with derivatives. You did this last year. This is how you calculated maximums and minimums, and you analyze them because the slope of the tangent line, or the derivative at this case, is going to be 0. So in the calculator, you can graph the derivative, hide the original function, and analyze this graph of the function. Take a look at this slide, kind of look at my hints. If this was done in class, I might flush this out and ask more questions. But don't forget, maxes and mins have horizontal tangent lines, hence the derivative. So I didn't show the derivative graph. If we were in class, I probably would graph this on my calculator. But I can make a prediction about this derivative graph. If this is m prime, this part of the graph is increasing, so this graph will have, the derivative will have positive values until it gets to this maximum. then the rest of this graph is decreasing. So that will be negative. So if you are analyzing this graph, this is the key moment where your derivative changes from positive to negative. Hence, you have a maximum because the original graph changes from increasing to decreasing. Remember, I do want to go back because I did the next 3 lessons, basically. Even though graphing calculators and computers have eliminated the need to routinely use calculus because they have this beautiful max feature, we will really study this a little bit deeper to understand a lot of different things about functions. So let's start with this word, absolute extreme values. Absolute extreme values are the maximums or minimum points on the curve. The word absolute is used by the AP test often, and sometimes, about 30% of the time, they will interchange the word global. You have to know that these words are linked. Absolute and global mean the exact same thing. They are the highest of the high point, and extremes could be low too. They are the lowest of the low points. Extrema is a Latin word which is plural, which means there might be more than one in case if they ever use that. Extremum is singular, one. Now, extreme values can also be found on the interior or endpoints. These endpoints are where it gets tricky, particularly in the story problems. This is our function y equals x squared, which is defined over an open interval forever, negative infinity to positive infinity. This has an absolute, and don't forget that is the same word as global, has an absolute or a global minimum. Some people will say 0, 0. That's okay, but if I ask you for the absolute minimum value, it's the y value, not the x. That would be like the highest mileage. That's the y value. In this case, it's the lowest value, which is the y value of 0. Even though these are both the same, you wouldn't get that wrong. Since there are no endpoints here, this goes up forever, we say it doesn't have an absolute maximum. By all means, if I am going too fast, you can stop this video. Now, what happens when you have a closed interval? When you have a closed interval, remember brackets means include. That's why this dot here is filled in. You do have an absolute minimum value. It's still 0. And you have an absolute maximum value. That value is 4. Where it occurs is 2 at x equals 2. So be careful because the AP exam may ask you for what is the absolute maximum value versus where does the absolute maximum value occur. And since these are closed interval and brackets here, filled in dots, you can actually say they have a. Well, what happens if one of the ends is open, like a 0? So how low does this function go right in there? Does it go to 0.1? What about 0.01? What about 0.0001? You see my confusion there is how low can you go? Because you can't go to 0 because this doesn't mean equals 0. It means greater than. That would be like saying x is greater than 0. So if you can't really start at 0, how low can you go? I don't really know. That's why you say none. But the maximum is a closed circle right there, and it does have a maximum value of 4 located at x equals 2. What about when they're both open? None. Very similar, same idea. You should have probably studied this a little bit last year, and you should be pretty proficient. That's why I'm doing this with a video, because it goes really fast, and I can get this done in minutes as opposed to sitting here and talking to you, because I have a tendency to ask lots of questions. The extreme value theorem is sometimes called EVT. It is one of the 3 theorems that may be referred to by name, but it is far and away the least popular. An extreme value theorem says if f is continuous over a closed interval, must be closed, then f has a maximum and minimum value on that interval. So if you look at these three situations, the maximum could be on the inside, interior, and the minimum could be on the inside. The maximums and minimums can occur on endpoints as long as the interval is closed. And you could have a situation where the maximum's at the interior point, but the absolute minimum, these are two minimums, there and there, but this one here is not absolute because this one's lower in terms of minimums. Then this would be the absolute/global minimum. This is the absolute/global maximum. And then local extreme values are a little bit different. These are local. These are not global or absolute. Local is used about 85% of the time. They will use another word interchangeably with local, and that's relative. Relative will be used much rarer, unlike global and absolute, which are more closer together in terms of percentages. That'll only be used about 15% of the time. So local is definitely becoming more popular these days. Local maximum is the maximum value within a smaller window or a smaller open interval. Same thing with local minimums, same idea. I'll explain the picture. So this here is the local maximum, but not the absolute or global maximum because this is higher. Changing colors to blue for minimums. This is a minimum. If this is a closed interval, this is a minimum. If this is a closed interval, this is a minimum. They are all local minimums, but the lowest of the low changes it to absolute. There is some confusion among math textbooks and math professors that say you cannot have a local minimum or maximum. You cannot have a local minimum or maximum at endpoints. That is debated, so they will usually not ask you for locals at endpoints. They will only ask you for locals in a specific interval, and you're looking in that range. But the way we define it through these slides in our textbook is a endpoint can be local, but don't really worry about it. And then here's another picture. I'd like you to notice something about the derivatives of this graph. Let's talk about all the locals for a second. We are calling this a local minimum, a local minimum, a local minimum, but the red is the absolute minimum because it's the lowest of those lows. Maximums. I'll try yellow here. Does this work? Yep. Maximum, maximum. There happen to be two. Which one's the highest of the high? This guy here, so that would be the global. Now I'm going to erase some of this, so let's take a look at the maxes and mins. The derivative here, the one I just erased, and the derivative here, the one I just erased, I'll put little arrows to them. One of them has a derivative of 0, and one of them has a derivative that's undefined. So basically for maxes and mins, you do have to verify the derivative, and the possibilities are 0, undefined, and the endpoints don't have zeros and undefineds, but they always must be considered. And you do that with something called the candidate test to determine which is lower. Is this one lower? Is this one lower? Is this one lower? We're going to do that with something called the candidate test by checking all the y values. Local extreme values. A function has a local max or min at an interior point, and if the derivative exists, if it does, on the interior points, then it has to be 0. So if I go back to that other slide that had this guy, that was like a corner, that derivative is not 0, but the derivative also does not exist. So just kind of like a little fact. Critical points, becoming more popular lately. There was a 10-year period where they were almost never asked for critical points, but now they're making a comeback. Critical points are points in the domain of the function where the derivative is 0 or does not exist. That's it. Very simple. Do they produce maxes and mins? Not always. Really? Why? Let's look. These are some examples where you would be finding absolute maxes and mins. So, for example, the work for this one, let me change to a color here. The work for this one is this is your function. Take the derivative of that function. Now, this is a simplified version of that function. So you have to know that the rational exponents, that's the cube root, and it has a negative exponent, so that means move me to the bottom. This is a better version to figure out when this does one of two things. Does it equal 0, or is it undefined? Well, first of all, this can never be equal to 0. Okay, never. So put anything in here in the bottom. Even if it's 0, you're going to get undefined. Oh, undefined! There we go, x equals 0. So undefined is going to be x equals 0, but anything you place in there, figure it out, cross-multiply, whatever you want to do, it's not going to work. So this is going to be a critical point of that function. The first derivative is undefined, so therefore we call it a critical point. This is defined over a closed interval. So you must check endpoints. Let's see if I have that on my next slide. I do. So I'm not sure what's happening to this function, but I know it has a critical point when x equals 0. So I wonder what the value is. This is on the regular function. This is called the candidate test. This is your first glimpse at it. It's very popular. I like the candidate test to be a table of values made up of my key points. A key point is 0. Why is that 0? A key point. Because on the last slide, the derivative was undefined. So I'm going to put every x value in here where the derivative is undefined or when the derivative is 0. But I want to check its value there. So if I plug in 0, the cube root of 0 is 0, 0 squared is 0, you get 0. Notice how I'm doing this table. Let's plug in negative 2 for x. So that would be f of negative 2 equals, here's your work right there. Using a calculator, you get 1.5874. And likewise, you plug in a 3. Why am I care about negative 2 and 3? Because those are the endpoints. You get 2.08. Now, if I create a very brief sketch, I know that 0 is 0. I know that negative 2 is 1.5 something. And I know that 3 is 2.08. So now I could do something bad, and that is just connect these 3 dots with a parabola. But if you remember correctly, the derivative at 0 was undefined, so it's more likely to have some sort of weirdness going on in the middle with a corner or a cusp. Absolute maximum, because it's the highest y value. Absolute minimum, because it's the lowest y value. And if you notice, you only care, I'm going to summarize this again because you'll hear me say it about 800 times, you only care about when the derivative is 0 or undefined and the endpoints. And that's how you do a candidate test. Okay, so this basically summarized what I had on the last one. And remember what that graph was. Remember it went from negative 2 to 3. And this is pretty much, and without even knowing what that graph looked like, I kind of had a good feel for it because I knew it was undefined there. Finding maxes and minimums analytically. I'll probably go too fast for you on this slide. You may want to pause it. Here's your procedure. This overlaps with probably the most important point-wise chapter of the year. First step, if you're asked for max and mins, is to find the derivative of the function, set it equal to 0, or find where it's undefined. Doesn't mean they're maxes and mins. It means they're possible maxes and mins. Find the value at each critical point. I would suggest using a table. You're going to see me use that. You're going to see the rubrics use that. Find the value of the slopes between the critical points. The reason why I do that is, remember that very first graph about mileage, the derivative looked like this. If you find the values or slopes for, that's derivative right here, slopes or derivatives. If you find the derivatives on the left of your critical point, and it is positive, and you find the slopes on the right of your critical point, the critical point I'm circling in red because the derivative is 0. Remember, this is the M prime graph. This will change from positive to negative. Positive means increasing, negative means decreasing. You know you have a max. And then comes number 4. On closed intervals, check the endpoints by using a table. That is key. The most often forgotten thing to consider endpoints. Look at the board next to my door. Number 2, check endpoints. And then I said this a couple times, but I didn't illustrate it. I'm illustrating it now. The derivative in the middle here is 0. Slope of the tangent line is 0. Yet it's not a, it is a critical point, but it's not a max or a min. The derivative graph, this is an increasing function. It would be positive. It starts to flatten out to 0, but it's increasing again, so it doesn't actually cross the axis. That's my F prime graph. So be careful, everyone. Just because you have an undefined, the slope of the tangent line is undefined, vertical tangent, does not mean you have a minimum either. That is your lesson for today. Thanks for bearing with me, and good luck. I'll see you next class for mean value theorem.